Hi, this is Mrs. Hickman, and in this video we're going to be going over slope fields and Euler's method. So first let's talk about a slope field. So a slope field or directional field is a graphical representation of the solutions of a first order differential function, which means you're looking at y prime. Okay. It is useful because it can be created without solving the differential equation analytically, which is what we did in the last video that I discussed. So we're going to be looking at this. So using a plot diagram, you're going to evaluate dy over dx using the points in the diagram. So to find what the slope on the fields are going to be, so you would be giving an x, -1. So this is the setup. So you have -1, 0, 1. So here are the columns, -1, 0, 1. And your y is going to be, so you see the y's are the same. You got 2, 1, 0, -1, 2, 1, 0, -1, 2, 1, 0, -1, 2, 1, 0, -1. And to find the slope of that, now these aren't all going to be the same thing. You're going to be actually given a point, dy over dx equals something, and that's how you're going to use it to find the point. Dy over dx is going to be this number divided by that number. Okay? When you get that, so if you get like dy over dx equals -2, you're going to draw something with a slope of like -2. Okay? Like that. So let's look at this. So the evaluated dy over dx is a slope at each point. So as dy over dx values get bigger, the slope is going to be steeper at that point, which makes sense because if we were looking at a linear function that's like y equals 2x versus y equals 4x, the y equals 4x is going to be a lot of a steeper line than y equals 2x because you have a higher rise over run. Okay? So if it's a proper fraction, the slopes are going to be flatter at that point. And this makes sense. Proper fraction would be like 1/2. So your rise is going to be smaller, but your run, or horizontally, is going to be wider. So you're looking at a slope of 1 over 2. So if you're confused at what I'm saying, you can compare a slope on a line. So let's say we got m equals 2x, or 2, and m equals 1/2. Okay? So we got a plot. 1, 2. So y equals 2x is going to be up 2 over 1. So it's going to look something like that. This one right here is going to be up 1 over 2. So it's going to be a flatter slope. Okay? If your slope is 0, so if your dy over dx is 0 in this line, it's going to be a horizontal line at that point. We know this because when we found the first derivative, that's where we found the maximum and mins on extrema. If dy over dx is undefined, the slope is a vertical line at that point. Okay, so let's construct a slope field for the differential equation. Okay? So if we can remember, this right here is r, this is theta. Okay? So dy over dx equals cosine of x. So this is a derivative. As we've seen in the other video, we were taking the antiderivative of these. So this is the derivative right here. So whatever this value is, whatever x is right here, that's what's going to be your slope. Okay? So let's look at this. So we got cosine x equals 0. So where x equals 0 of cosine, that is going to be the value. So where cosine of x equals 0, that's going to be at like the pi over 2's. So at the pi over 2's, so cosine of pi over 2's, or k pi over 2, your slope is going to be 0. Okay? Because cosine of pi over 2 is 0. Cosine of 3 pi over 2 is also 0. So if you want, we can go ahead and put these down. So we got the pi over 2, so everywhere on here you're going to have that. So on each line you got a 0 slope. So it's just going to be a flat line like this. And you're going to do this for each one where there's a pi over 2. 2 more. Don't forget your zeros. They count too. So everywhere on any pi over 2, the slope is 0. So that's 3 pi over 2 right there. Okay, let's look at the, and the top ones. Okay, so where's cosine equal to 1? Well, cosine is equal to 1 at x equals 0. Okay, because cosine of 0 is 1. So x, so you can see cosine of k pi over 2 equals 0. Well, cosine of 0 equals 1. So this is telling us where 0 is, the slope is going to be 1. So just try to do it a little bit. So you got up 1 over 1 type thing. So it's going to look something like that. Up 1 over 1. So you kind of make the line look like it's going to be a slope of 1. So up 1 over 1. So all of these should be slope of 1. That was a little bit steeper, but it's hard to see with the shadows I got. Okay? Now we got one more. Where cosine x equals negative 1. Okay? Where's cosine x equal negative 1? Oh, and also at the 2 pi's. Cosine, hold on, we're not done with this one yet. 2 pi's, or anything, the 2 pi is also 1. Okay, because when we go around the unit circle with year 0, go around, there's 2 pi. So it's also a slope of 1 here. Probably would be helpful if I was using a ruler or something so I can see it better. So you're acting like you're going here, but you're stopping at the dash. Okay, one more over here. Okay, so all these are slope 1. So if I was to keep going, it would be 1, 1, 1, 1. Right over here, so where's cosine equal to negative 1? Well, this is going to be at x equals k pi. But it's every odd k pi, odd k pi's. So k pi, where k is odd. Okay, so right here we got negative 1, so this is going to be a slope of negative 1. So you're going to be looking like you're making this line right here, except you're stopping right there. And the other pi is over here. Okay. Now watch, if I was to draw a line on anywhere, you kind of stay here. So I got that, so you just kind of follow your trail here. So we'll say this is 1 right here. That's negative 1, so here's your trail. Okay, so there's your sine graph right there. So it makes the sine graph automatically because you're looking for the slope. The slope of this is going to be a sine graph, or the antiderivative of this. Okay, because remember, this should be the sine graph, because if we were differentiating this like a differential equation, cosine x dx, so y is going to equal to sine x. That's what it's drawing. That's what these slope fields are helping us. And then these are telling you where the plus c's are. So let's say I started there, it would look like this. Like that. So these possible values are just where you see a c value. And you just follow along the curve. Okay, so there is that. All right, so now we're actually going to be doing an example with a differential equation. So for these, you almost have to do this because we don't know how to integrate that just yet. So when I told you about the x and y, the x's are always going to be the same. It's going to be -1, 0, or 1. So this is -1, okay, or y is going to be 2, 1, 0, -1. Okay, we're going to start with that one. So to find dy over dx, you're going to use this. So you're going to do 2 times -1 minus 2. So because x is -1 there, y equals 2. So you're going to have 2 times -1 minus 2. -2 minus 2 is -4. Okay? 2 times -2 minus 1 is -3. 2 times oops, that's supposed to be 1. I'm sorry. 2 times -1 is -2. 2 times -1 minus a -1 is going to be -2 plus 1, which is -1. So let's draw those slopes real quick. So we got -1, -2, -3, -4. So -2. And let's start at -1. So -1. So -1 is going to kind of look like this. Okay. -2 is going to be a little bit steeper. So you got -2 is up 2 over 1. Or up 2. So it's going to just be a little bit steeper. Okay, and then you got -3. That's going to be a little bit more steeper. And then you got -4. Okay, I know it's going to be hard to do these. Just if you're not sure, this is m equals -1. You can also do this. That's m equals -2. M equals -3, and that's m equals -4. Like, just tell me what it is on the left side so I know you're trying to figure out it. All right, this x is all the zeros right there. So you got 0, 0, 0, 0, 2, 1, 0, -1. Those don't change. So you got 2 times 0 minus 2. So 2 times 0 minus 2. -2. 2 times 0 minus 1 is -1. 2 times 0 minus 0 is 0. 2 times 0 minus a -1 is 1. Let's graph those. So we got +1 down here. Zero, -1, and then -2. So just a little bit steeper than that. Okay? So this slope is a slope of 1, 0, -1, -2. Last one. So this x value is 1, and then you have 2, 1, 0, -1. You're looking at the y values. So 1, 1, 1, 1, 2, 1, 0, -1. 2 times 1 minus 2 is 2 minus 2, which is 0. 2 times 1 minus 1 is 1. You do not have to show this. If I do a quiz on this, you do not have to show this part. I'm going to figure out that you're knowing what you're doing. 2 times 1 minus 0 is 2. 2 times -1 minus -1 is -2 plus 1. Oh. 0, 1, 2, 3. So 2 times -1 is -2. -2 plus 1 is -1. Okay, so let's do this again. So we got -1. Oh, this is supposed to be +1. Now I know I'm going crazy. 2 times x equals 1 minus y. So 2 times 1. So you got 2 plus 1, which is 3. That's supposed to be a 3 right here. There we go. Alright, so let's make a slope of 3. So there's kind of what 3 is. Trying to do a little muscle memory there. Slope of 2, a little bit flatter than that. So that's 2, 3, m equals 1. That's a little easier because you can kind of get a gander of. And 0. So that's your slope field. Okay, and on the handout I gave you, you'll have little things. Okay, follow the slope fields through the blue dot to help you out with 35 to 39 odd. Okay, so Euler's method. Description. So these are graphs, a solution to any initial value problem without knowing the equation. Now, initial value was the one where you found the differential equation by integrating both sides, and then you were given a point, and then you put the point in so that you could find C, and then you plug that into the general the particular solution was the general solution plus the value of C that you found using the points you're given. Well, here's a way to chart it. So the procedure, begin at point XY, specified by the initial condition. This point will be the graph as required. Use the differential equation to find the slope, dy over dx at the point. Then increase x by a small amount, change in x. Increase y by a small amount of y, where change in y is going to be dy over dx times change in x. This is going to define a new point, x plus change in x plus y plus change in y. So that's going to be the next point that you're going to write. Using this new point, return to step 2. Repeating the process, construct the graph to the right of the initial point. To construct the graph moving to the left of the initial point, repeat the process using negative values of change in x. So, return to step 2, blah, blah, blah. To construct the graph moving to the left from the initial point, repeat the process using negative values of x. Okay, that just means you go the other way instead of adding. Okay, so let's start here. So I made this chart. This is not going to be a test. You kind of got to know this design I got here. So x, y. So we have x equals 2, y equals 0. dy over dx is x plus y. Okay, so x plus y. So we got 2 plus 0 is 2. Great. Change in x. And they give you a change in x here of 0.2. That's not going to change. Okay? Change in y is going to be dy over dx times change in x. So you're going to be doing 2 times 0.2, which is 0.4. And then define your new coordinate of this field. You're going to do x plus change in x, so 2 plus 0.2, y, 0, plus change in y. So you have 2.2, 0.4. So you have here, and then you repeat there. You got 2.2, 0.4. So this process repeats the whole way. So now you got x equals 2.2, y equals 0.4, which is 2.6. Change in x, 0.2. That doesn't change. Change in y is dy over dx. So 2.6 times 0.2, which is going to be 0.52. Okay. New change in x coordinate is going to be 2.2 plus 0.2. New y is going to be 0.4 plus change in y, 0.52. And you get 2.4, 0.92. Okay. Also, if you're wondering when you're done, you are done when you hit f of 3. it's approximate f of 3. So when this number gets 3, that's when you're done. All right, your new x value was 2.4, 0.92 from there. Start the process over. X plus y, 2.4 plus 0.92 is 3.32. Change in x is 0.2. Change in y is 3.32 times 0.2, which is 0.664. X plus change in x is 2.4 plus 0.2, which is 2.6. Y is 0.92 plus change in y, which is 0.664, which is going to be 1.584. Okay, we're almost there. We got to get to 3. And you get 2.6, 1.584. dy over dx is x plus y, so you got 2.6 plus 1.584, you get 4.184, which consequently has nothing to do with this, but that's a specific heat of water. Change in x, 0.2. Change in y is going to be dy over dx times your change in x value. So you have 4.184 times 0.2, which is 0.8368. X plus change in x is going to be 2.6 plus 0.2, which is 2.8. Y is going to be 1.584 plus 0.8368, which is 2.4288. And that's 2.8, 2.4288. Oops, I'm going over. X plus y, 218 plus 2.4288. So 2.8 plus 2.4288 is 5.228. 0.2. dy over dx is 5.228 times change in x, which is, so this times that, 1.04576. 2.8 plus change in x is 3. Yay, that's f of 3 right there. And change in y is 2.4288 plus 1.04576, which is 3.47456. So f of 3 equals 3.47456. So yeah. So Euler's method is a graphs the solution to any initial value problem without knowing the equation. There you go. That's how you figure that one out. Let's do a negative x and then we will be done. Euler's method. I'm probably not going to go through all of these. Okay. xy. So xy, 2, 3. dy over dx is x plus y. Or that's supposed to be 2x minus y. 2x minus y. That's going to be a 2 minus 3. 2 times 1. Your change in x is negative 0.1. And change in y is going to be dy over dx. So 1 times change in x. This is 0, 1. X plus change in x. 1.9. 2.9. And for here, you're going the whole way to approximate y if x equals 1.5. So 1.9 and 2.9 goes here. Okay. 2 times 1.9 minus 2.9. 2 times 1.9 minus 2.9 is going to be 0.9. Change in x is negative 0.1. Change in y is 0.9 times change in x, which is going to give you negative 0.09. And x plus change in x, so 1.9 minus 0.1 is going to be 1.8. And you get 2.81. And then you go over here. And I think y'all get the drift, but I'm going to show you the answer here so you can just check your work, so to speak. Okay, so there's the answer to that one. And this concludes slope fields and Euler's method.